Hello everyone, my name is AIDAqc and I'm a PhD student from the University Hospital of Cologne, and this video is a video to guide you through the steps to use AIDAqc, a quality control tool for preclinical MRI images. So basically these are the steps that we will go through them with each other, and we can start doing it by going through the GitHub page of our group. That's the Ascent Lab GitHub page, and then we go into the repositories. We find AIDAqc. There are multiple ways to do it. You can only directly clone it with the HTTPS link here, or you can also download the zip file as you want. So basically I will clone it here now with the HTTPS link. I will go into my testing data. I will open git bash. You can also use any other terminal. I'm using datalad, but you can also use git. I clone it, I paste the link here. Now I have cloned the dataset, and this is now basically the only script that you need from this repository is the parsing data, and I will start using an Anaconda terminal. So I have created Conda AIDAqc. Conda activate AIDAqc. Now basically before you can work with this, you need to install the requirements, of course. Better it is to be in a separate Conda environment like I have here now. I have this Conda activated, and I won't do it now in this video because it takes too much time, but basically you can do Conda install -n requirements, I think, and here all are the requirements that is needed for this pipeline. After you have installed them, you can go into the directory. I'll do it like this now, and with cd, and then now I can do Python parsing data. This should work now, and for the beginning you can just try it out with the --help to see if you have installed everything. Now then it should come up with a page like this. So you have to input the output, the format type, which can be RIFTY or raw data, so RIFTY MRI data or raw Bruker data. The -s is suffix, and the -e is an exclude, which I tell you in a couple of minutes. Now basically what we do now is -e, and then we give it the address of our data. Our data is now this one. This is just a data set that I've downloaded from neuroinformatics data, so to say, but it's MRI data. In it we have anatomical data. These are normal anatomical data, like this one here. And of course the resting state data. This we have here also. This program which I'm using is AIDAqc Snap, just a normal image view program. So basically we want to give any folder that is containing the data. It will automatically parse through all of the folders and subfolders, so you don't have to worry about any kind of substructure that you have here, but it is better if it's in the bits format. So if you hold shift, then you can copy it as pass and you paste it here, and then we want to have an output QC now, for example, and I drag this here. There are multiple ways that you can do this with this path. I could also have dragged the file before here, but I do it sometimes just how I feel like it. So now if you would have here, for example, a new folder, this would be created automatically. So you could also add as many subfolders as you want, but this is okay for me. Then I want to do -f. I want to specify nifty, Then I want to do a suffix which I don't need right now, but only that you know what I mean here is, for example, here the only thing that is available is now this subject. But for example, you have multiple processed files here which you don't want. You have sometimes masks, you have stuff that are nifty files, nifty.gz files, but you don't want them to be included in this quality control procedure. You can add, for example, everything that is attached to this .nifty. So for example, if I would do now T2 weighted, then it would only take anything that has T2 weighted behind it. If, for example, you only want to do the anatomical data and not the functional data, then this would be actually an option to do so. Also, with -exclude, you can set specific words, but this words doesn't need to be at the end. It can be anywhere in the past. So, for example, you have a specific folder which is full of some nifty files that you don't want to register. For example, I don't want this folder. Then I can do -e and I put this here, and this won't be in the processing of the quality control. But as I want everything, I won't do it now with these two options. This is fairly what you need. Enter, and then it will start. So the first thing that is, it parses through all of the files. Then it goes to the second stage where it starts calculating. You have a progress bar. Sometimes it goes faster for the anatomical data, but for the functional data it takes more time as they are 4-dimensional. But I will keep this running. Just for the time, I will show you how the output looks like. Now here we have this manual slice. This is the folder that I've created now. Here we have the manual slice inspection folder, which while it processes the data, it makes a snippet of the middle slice, and if you have a fourth dimension like resting state data or diffusion weighted data, it will also take the middle volume, just for the user to see the data as it goes, so to say. And it is kind of a progress bar itself, so if the user can see that it creates data there, then you can follow it as it goes, and you can see with the first glimpse also an image of that file that you have. Now this is the same, this is after it's got finished. Mainly we start with this one here, so the calculated features. We have the anatomical and the functional, where you have the file address here. You have the corresponding image that you could like take this, copy it, and you can go into this one and then just search it, so to say, and it will pop it up for you to fastly find that data. Or for example, you can take this one and you can also put it here from the dataset. Here it is. And now we have here different, like these are our features. You can use the filter function here, and for example I have two different SNR methods. These are the spatial resolutions in X, Y and Z direction. So in the Z direction I call it slide thickness, so spatial resolution in the Z direction is the same as the slide thickness. And then you can see that you have some variety here between the data. For example, now you can also sort from smallest. This is now the lowest. This subject got the lowest SNR, for example. Then you can, for example, take this and here put it directly in here. So, and this is the file now, because this file hadn't a proper header file. This is like not shown very nicely here, but this is a problem of the data, and you can directly go and look at this data and see what has happened to its header. And Yes, that was the first thing. So if we have the anatomical, then we have also the functional data, of course. This is similar, but here, for example, we have TSNR, and we have a displacement factor, which is the standardization of the mutual information. So I have calculated the motion that is happening in the force dimension or in the time dimension with the help of mutual information, and this is the standard deviation of the mutual information of one reference image, meaning that the higher this STD of the mutual information is, means that more motion has happened here. For example, in this subject here, if we look through it, this has the most motion. Of course, this is not compared to the rest. This was the part of the features that are calculated. Now we have another part, which is the voting CSV. For the voting CSV, this is the outlier detection algorithm, which uses 5 different outlier detection methods. Basically, one is a purely statistical method, which is the based on the interquartile range, and 4 are machine learning approaches, which use multiple features like 2 SNR methods and the TSNR and the motion, for example. But of course it does that for anatomical and functional data separately, but it always looks it relatively. So keep in mind, you never have a fixed, so if most of your data have a general bad quality, it again will find or detect those data that are an outlier relative to the whole data set. And for example, here we have some that got a value of 4. What is the meaning of this number now? 4 means that 4 methods of these 5 statistical outlier detectors, 4 of them have said that this is actually an outlier. The idea is that you have this majority voting approach, so that if all of them, or if many outlier methods say that this subject or this image volume is not good or is different than the others, then the probability that it really is an outlier is much higher, so to say. It lists here only those that at least got one flagged outlier from one of the methods. So if it is not all of the files here, it is only those that have gotten at least one voting from the 5, let's say, judges. For example, I will go into the functional here as a functional, and this one has gotten 5. Let's take a look at this one. And we can already see on the image it is not that good, but we can also look at the whole data set. And if we look at it here, we can see compared to the rest, it has lots of ghosting here, and it is actually very noisy in the sense of ghosts and probably also motion. Let's see. Yes, also motion. It is very I went through the fourth dimension and you can see the jumps that is happening in the fourth dimension. So it has motion and it has this artifact. So you can see that this 5 here of the voting outlier is actually justified. Now for the user, which to use as a threshold, this is depending on what your question is and how strict you want to be with your quality control. You can, like the 5s and the 4s are of course worth looking at. Something has happened there, but the 3s, 2s and 1s, you can look at them again and decide for yourself. So if you want to automatize this in a script, for example, that you take the 5s out automatically, you can do that, but generally I always suggest to always check them again, like I did now, to get sure and to actually see the problem and maybe decide for yourself if the problem is solvable or correctable or not. For example, motion up to 1.5 pixels can be corrected fairly good, but higher you can think about discarding the data. Now this takes a little bit more time, as you can see, but this was it actually for now. I think, of course, the QC figures, this is also interesting. Now, only for a statistical approach, you can also see these kind of plots. So you have your keep and discard. This is only based on the one outlier approach, which is a purely statistical one. And here it shows these two subjects that are out of this threshold, and you could look at them by only going to the calculated features. Anatomical was this now, yes. And if you would, this is now the normal one, so if you sort it, smallest to largest, now you can see this 1 and 3. 1 and 3, yes. These two subjects are these two. Now you can see now this kind of distribution here. You have this also for the other features. Figures here. For example, for displacement, we see that we have here not a Gaussian distribution, but here it is fairly well. We have some outliers here, but again, be aware that this is only based on the one statistical outlier detection and not using the machine learning approaches to it, which combines all of it looks at the features all together. This is only a statistical approach, which might be sufficient for your use case, but maybe not. This got now a little bit messier because we have so many different spatial resolutions, but again, this is informative in a case where you want your resolutions to be very homogeneous in your data set and you don't want to have different resolutions. Then you would look for clear circles here so that you don't have an image which has different resolution. That was it actually. If you have any other questions, you can write it in the discussion in our Aspen Lab GitHub channel, and there are also some information down here. Yes, that was it actually. So thank you for listening and for your interest. If you have any questions, you can contact me, of course, via email or in the discussion. Have a nice day and goodbye.